Good morning. It's a special honor to be invited to speak at the Shannon Centennial, especially in University of Michigan, where Shannon did his undergraduate, and I'm sure that the quality of the undergraduate had a lot to do with what he did later. So it says a lot about University of Washington, of Michigan. So my talk today will be about application of information theory to randomness generation. Information theory was invented by Claude Shannon in 1948 as a mathematical theory of communication. At the time, people were confused about what communication is, and there was general belief that one cannot communicate reliably over a communication or a noisy communication channel at a positive rate. And Shannon single-handedly and completely transformed the field of communication. So he defined communication simply as the fundamental, he says the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. He then proceeded to he proposed the general architecture of a communication system and proposed simple but very powerful probabilistic models for the source and the channel, which are the main components in his architecture. He then established the fundamental limits on communication. And then he defined the entropy as a measure of information for the source, and showed that it is the minimum rate of compression. And then he established the limit on communication, which is the highest rate of reliable communication, as the capacity, which is the maximum mutual information, and which can be strictly positive. And then last but not least, he showed that the source can be communicated over a channel if and only if its entropy is less than the capacity of the channel. And a consequence of this theorem is that one can use bits as a universal interface between the source and channel. You can compress the sources without any regard of what channels they will be communicated over, and you can design error-correcting codes for channels independent of what kinds of sources will be communicated over it. And this is exactly what we do today, of course. Okay, so the Shannon theory, of course, had a huge impact on practice, as we all know, and there are many people that spoke about the significance of his work, but one of my favorite quotes is by James Gleick, who recently published a book called The Information. And that quote was in the New Yorker, April 30th, which is Shannon's centennial birthday. And so he says, Einstein looms large, and rightly so, but we are not living in the relativity age. We are living in the information age. It's Shannon whose fingerprints are on every electronic device we own, every computer screen we gaze into, every means of digital communication. He is one of these people who so transformed the world that after the transformation, the old world is forgotten. So I think this captures Shannon's impact in a very, very strong way. Okay, so soon after Shannon proposed or put forth information theory as a theory of communication, a lot of people were fascinated by the notion of measuring information using the entropy and its implications. And much of the work must have been so bad that Shannon was compelled to write an editorial called The Bandwagon, in which he says information theory has in the last few years become something of a scientific bandwagon. Starting as a technical tool for the communication engineer, it has received an extraordinary amount of publicity in the popular as well as the scientific press. As a consequence, it has perhaps been ballooned to an importance beyond its actual accomplishments. Applications are being made to biology, psychology, linguistics, fundamental physics, economics, and the theory of organization, and many others. But then Shannon admits that information theory will have applications outside communication. So he says, I personally believe that many of the concepts of information theory will prove useful in these other fields. And indeed, some results are already quite promising, and so on. So my talk today will be about an application of information theory outside of communication, but I think it's an application that is where information theory comes out very naturally. And the application is randomness generation. And what I mean by randomness generation is generating random variables with prescribed distribution from coin flips. Randomness generation is has several important applications in simulation, randomized algorithms, and cryptography, and perhaps other areas as well. It also arises in answering fundamental questions that have to do with notions and measures of common information or correlation, secrecy, and classical and quantum channel synthesis. And the question that I'm going to focus on in my talk is what's the minimum amount of coin flips needed to achieve the desired generation, randomness generation. As we will see, entropy and mutual information will arise naturally as limits and bounds for the minimum amount of coin flips. And the proofs use information theoretic techniques. So my talk is in three parts. The first part, I'm going to talk about the basic, which I call centralized randomness generation. And the randomness generation could be either one shot using a variable number of coin flips, or asymptotic using a fixed number of coin flips. The second part of my talk will be on distributed randomness generation. Here is when I want to generate random variables at different locations. And again, we're going to talk about the asymptotic setup and then the one-shot setup. And in the one-shot setup, I'm going to talk about some recent results that we have. The third part is channel synthesis, in which we have a new ingredient, which is the use of communication to perform the desired randomness generation. And as we will see, there is a trade-off between the amount of common randomness between the agents and the communication that is needed to do the generation. Again, there will be an asymptotic version and a one-shot version. Okay, so the first setup I will talk about is the one-shot randomness generation. Here we have a source of randomness, which outputs W1, W2, and so on. And it's a sequence of IID Bernoulli half or fair coin flips. And what we would like to do is use the coin flips to generate a random variable x with some prescribed probability mass function P of x. We allow the generation to be performed using a variable number of random bits W sub I. And so in order to do that, we need a way for the generator to know when a code word ended, and to generate the corresponding value of x. To do so, we use a prefix-free code in which no code word is a prefix of another code word. And this is the same type of codes that are used in zero-error compression. So here is an example. Suppose you want to generate a Bernoulli 1/3 random variable out of fair coin flips. then here is one code that can do it. If you observe, the generator observes W1, and if it's a 0, then it outputs x equals 0. And if it's a 1, then it doesn't output anything, and it waits for the second coin flip. And if the second coin flip is a 0, then it outputs x equals 1. And if it's a 1, it waits and then repeats the process again. You can convince yourself that the generated x using this tree is Bernoulli 1/3. Note, however, that the variable length code we're using, the code words, of course, are the leaves, and so no code word is a prefix of another. And you can convince yourself that, you can observe that we need unbounded length code words to achieve this generation. Okay? All right. So now, let L be the number of bits, random bits that we need to generate x. And the question is, what's the minimum expected length L? What's the minimum expected number of bits that we need? In 1976, Knuth and Yao showed that the minimum expected length is within 2 bits of the entropy of the random variable you would like to generate x. And h of x is the expected minus log p of x. And in this context is a measure of randomness of x. In communication, it's a measure of information, but information and randomness are very tightly related, of course, when information has no, when the meaning of information is not considered. Okay, so let's go back to our example. So we can easily compute the expected length for the code that I used here, and it's 2. And the entropy of a Bernoulli 1/3 is 0.9183, so it's within that limit by Knuth and Yao. Okay, so now suppose that you're not happy with, suppose that you would like to generate a vector of IID random variables x, and that each distributed according to p of x. And you want to use a fixed number of coin flips W super NR, which is IID Bernoulli half NR bit sequence, to do that. Now, if you insist on using a fixed length, a fixed number of coin flips, then it may not be possible for you to generate the sequence you want exactly. And as we've seen in the previous example, the code words, the length of the code words may have to go to infinity in order to generate the desired random variable. And so what do we do? So what we do is we say, okay, let's generate that sequence such that, in some sense, the distribution of that sequence approaches the product distribution with the prescribed p of x as n goes to infinity. Okay? Now, specifically, we want the total variation distance between the distribution of the generated x, which I'm calling x hat here, and the product distribution to go to 0 as n goes to infinity. And the question is, what's the minimum randomness generation rate R in terms of bits per symbol generated? It turned out that that minimum R is also the entropy of x. So you can show this using a random coding argument, which is very commonly used in information theory. And so basically, you generate code book of 2 to the nr sequences, x of n, that are generated independently of each other, and each one is generated according to the product distribution for p of x. And then after you generate the code book at random, you give it to the generator. So the generator knows what the code book is. Now, when the generator observes a sequence W, it basically outputs the x hat equals to the xn with that index W. Okay? So we can show that the expected total variation distance, expected value of the total variation distance goes to 0 over, this is the expectation over all codes, goes to 0 if R is larger than the entropy, and therefore there exists a sequence of codes with total variation distance that goes to 0 if R is bigger than the entropy h of x. And this type of existence proof extends to distributed generation settings very nicely. Okay, so to summarize, for the centralized randomness generation, in the one shot, we saw that entropy is the limit, and it's the same as for zero error compression. And both zero error compression and the randomness generation, the one-shot randomness generation, use optimal prefix-free codes. For the asymptotic case, entropy is still the limit, which is the same as for lossless compression. And we can achieve it using random coding, which is a key technique in information theory. It's the probabilistic method, basically. And in particular, we see that the same limit, that for one shot or asymptotic, we get the same limit, which is the entropy, which is kind of interesting. Okay, now I'm going to move to the second part of my talk, which is in distributed randomness generation. First, I'll talk about the asymptotic setting, and then I'll talk about the one shot and talk about some recent results. Okay, so what's the setting for the asymptotic distributed randomness generation? Here we have, again, we have a common randomness source, which produces a sequence of IID Bernoulli half NR bits. And we're given some prescribed joint distribution between x1 and x2, which is p of x1, x2. Now, Alice and Bob each has unlimited independent local randomness, and their local randomness is the local randomness, as I said, is independent of each other and is independent of the common randomness. And Alice wants to generate x1 of n, and Bob wants to generate x2 of n. These are sequences, and what they would like is that the total variation distance between the joint distribution of x1 hat and x2 hat approaches that of the product distribution with the prescribed p of x1, x2. And the question is, what's the minimum common randomness rate R in this case? Okay, so there is, Alice and Bob have no communication between them. They are sitting in different places. The only common information they have is that random sequence of NR bits. And they want to generate x1 and x2 that are correlated with some prescribed distribution p of x1, x2. Okay? So in a seminal paper in 1975, Wyner showed that the minimum rate is given by the minimum of the mutual information between x1 and x2 and some random variable u, which represents the common information. And the minimization is over all distributions, which of course of x1, x2, and u, such that the joint distribution of x1 and x2 is still p of x1, x2. And x1 to u to x2 form a Markov chain. And the reason for the Markov chain is u is the only common information between x1 and x2. So given u, x1 and x2 are conditionally independent. Later, the this quantity j of x1, x2 was called the Wyner common information. It measures the amount of common, in some sense, it measures the amount of common information between the two random variables x1 and x2. Okay? Okay, so in case you don't know what mutual information is the difference between the sum of the entropies of two random variables x and y and their joint entropy as one big random variable x comma y. To understand the meaning of mutual information a little better, we can rewrite it as the difference between the entropy of x and the entropy of x after it observes y, the conditional entropy of x after it observes y. So what that means is that actually we can also do it, I repeated this. We can do it as h of y minus h of y given x. So it's the amount of information that y gives you about x, or the amount of information that x gives you about y, and they're both equal. And therefore, you can view mutual information as yet another measure of common information, and you can actually make that kind of operational as well. Okay. Now, it's not difficult to see that mutual information, just from the definitions of these quantities, mutual information is less than or equal to the Wyner common information is less than or equal to the minimum of the entropy of x1 and the entropy of x2. Okay. Now, the last one here is obvious because if you send x1 to both to Alice and Bob, then of course Bob can generate x2, and so on. All right. We'll come back to this inequality a little later. Okay, so now I want to just show you how Wyner proved the achievability of this result, which means that if R is bigger, if the rate R of randomness generation, common random generation, is bigger than the Wyner common information, then we can find sequence of codes such that the total variation distance goes to 0 as we want. So the proof uses random coding. And here I don't know of any other proof. So in the case of the centralized case, you can actually take a variable length code and chop it off and make it into a fixed length code and then prove the same thing. But in this case, there is no such alternative proof. So basically, let P of u, P of x1 given u, P of x2 given u, be the distribution that attains the minimization in the Wyner common information. And what we're going to do is we're going to generate a code book of u, 2 to the nr sequences of u. Each, they're independent of each other, and each is generated according to the product distribution P of u. And then we're going to give the code book to Alice and Bob before communication. And now the source, which is a random, the randomness, the common randomness source, outputs some sequence W, some index W, in this case, what we do is Alice, and it's given to Alice and Bob, and then Alice and Bob recover U, and then Alice generate x1 using the product of P of x1 given U, and Bob generates x2 using the product of P of x2 given U. So, and the question now whether this actually works. So, from the result for the asymptotic, centralized asymptotic case, we know that R bigger than the entropy of U. All I have to do is make sure that Alice and Bob know U. So if R is bigger than the entropy of U, then we're in good shape, and that scheme will work. However, Wyner showed that only R bigger than the Wyner common information, which is definitely less than h of u because of the way entropy is defined as h of u minus h of u given x1, x2. And the proof uses a covering lemma, which is similar to the one that is used in lossy compression. The converse, which says that R must be bigger than or equal to the Wyner common information, uses information theoretic inequalities, and I'm not going to get into it. But it's still very information theoretic. OK, so now I'm going to switch to the one-shot distributed randomness generation. Here, again, I have source of common randomness that produces IID Bernoulli half sequence, W1, W2, and so on. And then I have a generator that, upon observing the sequence, outputs some common randomness W, which is observed by both Alice and Bob. And this is the, we use a variable length code in this case, and so the code has to be prefix free. And then from W and from their own local randomness, Alice and Bob would like to generate x1 and x2 with the prescribed, exactly with the prescribed distribution P of x1 and x2. So it's a very basic setup. And let L be the number of WI bits that is needed to generate W. And the question is, what's the minimum expected L needed to be able, for Alice and Bob to be able to generate x1 and x2 with this prescribed distribution? OK, so by Knuth and Yau result, we can show that the minimum expected length is within 2 bits of what I will call the common entropy between x1 and x2. And the common entropy is simply the entropy of the common randomness W. And it's minimized over all distributions such that x1 and x2 have the prescribed distribution. And x1, W, x2 form a Markov chain. And again, the reason they have to form a Markov chain is because the only thing in common between Alice and Bob is W. All right. So this is yet another measure of common information. The common entropy is another measure of common information in addition to mutual information and the Wyner common information. G of x, however, is quite difficult to compute because it's minimization of a concave function over a non-convex set. So extremely difficult to compute, except for simple cases. If x1 and x2 are discrete, then we can easily show the following sequence of inequalities: that the mutual information is less than or equal to the Wyner common information, is less than or equal to the common entropy, is less than or equal to the minimum of h of x1 and x2. So the common entropy is bigger than or equal to Wyner's common information and is still less than or equal to the minimum of h of x1 and x2. Okay? And all inequalities can be strict. To see that, we look at the following very simple example. So here, x1 and x2 are both binary, and their joint probability mass function is described by this picture. x1 is Bernoulli half, and when I send a 1, x2 is a 1 with probability 1 minus p and a 0 with probability p. And when x1 is 0, x2 is 0 with probability 1 minus p and 1 with probability p. OK, in this case, we can actually explicitly compute g, j, and I. And I have them plotted here for p between 0, where the x1 and x2 are completely dependent, and p equals a half, where x1 and x2 are independent of each other. As you can see, For p bigger than 0 and less than a half, g is strictly bigger. I mean, h, which is 1, is bigger than g is, and then g is bigger than j, and then j is bigger than, strictly bigger than I. So all the inequalities can be strict, which means that the common entropy can be, in fact, strictly bigger than Wyner common information. Recently, we became quite interested in the continuous case. So now suppose x1 and x2 are continuous. And again, the setup is exactly the same as before. We have random bits coming in. The generators output some random variable w. And Alice and Bob would like to generate x1 and x2, which are now continuous. And what got us interested in this question is, what is the, can one generate two continuous random variables in a distributed way using only a finite expected number of coin flips? It's not clear what the answer should be here because they are continuous, so the entropy of each of them is infinity. Right? Okay, so in this case, we still have the inequalities. I is well-defined, j is well-defined, and g is well-defined. And we still have these inequalities. However, we don't have an upper bound here because the entropy of x1 and the entropy of x2 are both infinite because the random variables are continuous. So let's take an example. Suppose x1 and x2 are Gaussian. So I'm asking the question, can I generate two jointly Gaussian random variable using only a finite number of common? So can I capture the correlation between two Gaussian random variables using only a finite number of random bits, average number of bits? So here the Gaussian has the standard deviations are 1, and the correlation coefficient is strictly less than 1, between 0 and 1. Here we can compute the mutual information. We can compute the Wyner common information, and they are both finite. And the question is whether G is also finite. Now you can look at this question. This question is really not that obvious, because the first thing that you want to do is take the U from the Wyner common information and use it. But if you take the U from the Wyner common information, you get an infinite. G is infinity because it's a Gaussian. So then you say, OK, why don't I just quantize U and use the quantized U? Well, if you quantize U, then you destroy the Markov chain relationship, and you may not be able to generate them anyway. Exactly, because we want exact generation. So as I said, the answer is not completely obvious. So we showed that for x1 and x2 that have log-concave probability density function, the common entropy is between the mutual information and the mutual information plus 24 bits. And so there is a gap between, there's a finite fixed gap between the mutual information and the common entropy. This inequality is also interesting because it provides an upper bound on the Wyner common information, which is also not very easy to compute. Again, in terms of a gap with the mutual information. And this results in extensive generation of n continuous random variables. So it doesn't have to be just 2. But it doesn't have 24. It has something else that I will show later. So I'd like to talk a little bit about how we prove this result. So the first step is we prove the result for x1 and x2 uniformly distributed over some subset in the plane, in R2. We construct W using a dyadic decomposition scheme. And then we bound the entropy of that common randomness W by mutual information plus a constant for when S is convex using some quantity that we called erosion entropy. We then extend the proof to general probability density functions. We apply the scheme to uniform over positive hypograph of the PDF, and then we bound G by I plus 24 for log-concave PDF. So let me give you a little bit of more information about this proof. So let's now assume that x1 and x2 are uniform over some subset S, and let's define the dyadic square as a square with side length 2 to the minus k for some k integer k, and left lower corner 2 to the minus k times nu, where nu is a vector of integers. So the dyadic decomposition scheme that we're going to use in our proof partitions the set S in R2 into the largest possible dyadic squares. So let me give you an example. So let's take this ellipse, and let's see how the dyadic decomposition for this ellipse would work. First, for k less than 1, you can convince yourself that there is no dyadic square. It can be inside S. It's too big. Okay. Now, for k equals 1, we have 4 dyadic squares inside the ellipse. For k equals 2, we have these yellow squares. Of course, we are not going to cover the squares that the area that we already covered previously. And then for k equals 3, you get these squares, and so on and so forth. And in general, you will need an infinite number of dyadic squares to partition this ellipse. Okay. So how do we construct the common randomness out of the dyadic decomposition? Here is what we do. We define W sub d to be the square that contains the random variables x1 and x2. Okay? Now, conditioned on W, x1 and x2 are uniformly distributed over the dyadic square, which means they're independent of each other. And of course, x1, WD, x2 form a Markov chain. So what that means is that I can definitely use this W in my scheme. And of course, the entropy of this W will give you an upper bound on the common entropy because, of course, it's just a scheme. It's not, there's nothing, it's not necessarily equal, obviously. Okay, now what do we do next? What we do next is, how do we generate this WD? We generate it using a prefix code, just like I described earlier for the centralized one-shot case. And so you assign code words to the dyadic squares. And then you give the dyadic decomposition and the code to all parties. Now, the generator only needs to know the code. It doesn't need to know anything about dyadic decomposition, but Alice and Bob need to know the dyadic decomposition. All right, so now here is the scheme then that I will use to generate x1 and x2 uniform over a subset of R2 in a distributed way. All right, so first the generator, common randomness generator, observes some code, and then it outputs the W, the square that corresponds to that code. Now, Alice and Bob both know the square. And now, Alice generates x1 uniformly over this side of the square, and Bob generates x2 uniformly over this side of the square. And it's not difficult to see that x1 and x2 will have the desired joint distribution. So here I'm plotting the empirical value of the entropy of this random variable for the dyadic decomposition in the blue here. And this is the mutual information, and we're plotting them for ellipses with different widths. As you can see, this graph suggests that there is a gap between the mutual information and G over less than 6 bits. Of course, the general theorem that I mentioned says 24 bits, but this is more general for all log-concave PDFs. Of course, that example is a log-concave PDF. It's convex because it's uniform. All right. OK, so now let's talk about how we found the bound. So to find the bound, let's look at the definition of the entropy of this random variable that we created, the dyadic decomposition created. Well, it's simply the expected value of minus log of the area of the square over the area of the set S. Now, the area of square is LD square, with LD is the side length of the largest dyadic square that contains x1 and x2. Rearranging terms here, we get this equation. Now, doing anything with the expected value of minus log L sub d is very difficult because the distribution of L sub d is incredibly nasty. It has to do with how you did the dyadic decomposition for the set. So instead, we bound it using an easier quantity to deal with, which we call the erosion entropy. We define the erosion entropy in a more general way in our paper, but for the purpose of this application, it's basically the expected value of minus log of the side length of the largest square centered at x1, x2. So here is the x1, x2, and you draw the largest possible square that is still inside that set. Okay. After some work, you can show that basically the expected value of minus log L sub d, which is this quantity here in terms of the entropy that we're interested in, is less than or equal to the erosion entropy plus 2. OK, now we can go further. Up to this point, I didn't make any assumptions about the set S. But if the set S is orthogonally convex, which means that each axis-aligned line is connected like this, then we can show that the erosion entropy is upper bounded by log of the sum of the width area of S plus some constant. Now, previously, what we're interested in is really bounding the entropy of W for the dyadic decomposition. So now we substitute from this lemma 2 into here, and we get this bound on the entropy of the W, the dyadic common randomness. And this bound depends on the perimeter in some ways, depends on the perimeter to area ratio of S. So if S has high perimeter to area ratio, like this, for example, then you get very high H of W. But we can do better. We can pre-scale x1 and x2 before we perform the dyadic decomposition into x1 tilde, x2 tilde, which will also be uniform over S tilde. We scale it so that L1 equals L2 for that new set, the scaled set. And then we perform the dyadic decomposition on this set. Then Alice and Bob know the scale factors, and so they can recover x1 and x2. So this gives us a tighter bound on the entropy, but now it's the entropy of W tilde after we did the scaling. And here we can see that this is smaller, this quantity here is smaller than this quantity, simply because the geometric mean is less than or equal to the average, to the arithmetic mean. Okay? So this is a better bound than this other one. Okay, so now up to now we haven't seen mutual information show up anywhere in a bound. And it doesn't show up in general. It shows up only in a specific case. So, so now we have this bound on HW tilde. We also can expand the mutual information as the sum of the differential entropies of x1 and x2 minus the joint entropy, which is because the random variables are uniformly distributed over S, it's log the area, minus log the area of S. Now we subtract the two equations, and we get this bound here on HW in terms of a mutual information, and then we have these two terms. And if S is convex, then one can argue that the marginals, which determine h of x1, are close to uniform, and therefore these two quantities are very close, can be bounded by some constant, and we get a constant gap between HW tilde D and the mutual information. Okay, now how do we generalize this scheme to arbitrary probability density function? To do that, well, let's consider the positive part of the hypograph of the PDF, which is the volume under the PDF bounded by the x1, x2 plane. And then we call that it's the all points x1, x2, z, such that z is between 0 and the PDF. So the key observation is that if we let x1, x2, z be uniform over the positive part of the hypograph, then x1 and x2 have the right joint PDF. And therefore, we can use the dyadic decomposition scheme to the uniform over the positive part of the hypograph. And it's now three-dimensional instead of two-dimensional, but everything generalizes fine. Okay, and if F is log-concave, then the positive part of the hypograph is orthogonally convex. We can then do lots of work and end up with the final result that I mentioned. And the result can be extended to n agents and replacing the mutual information with the dual total correlation defined here, and then replacing 24 bits with n squared log e plus 9n log n. Okay, so to summarize the distributed randomness part, for the asymptotic case, Wyner common information J is the limit, and we use random coding and similar covering lemma to the lossy compression. For the one-shot distributed randomness, common entropy is the limit, and common entropy is within a constant of mutual information for log-concave BDF. And the common entropy can actually be larger, so the limit can be larger for one shot than for asymptotic, which is different from what we had for the centralized case. And the common information has several different measures. Mutual information is one, Wyner common information is one, and the common entropy is one. Okay, so that brings us to the last part of my, talk, which is on channel synthesis. First, I'll talk about the asymptotic, then about the one-shot. So here is the asymptotic channel simulation with common randomness setup. Alice observes a sequence of random variable xn, and Alice and Bob have unlimited amount of common randomness in between them. Alice sends a message m, chosen from 1 to 2 to the nr to Bob, who then generates y. And what we would like that the joint distribution of xn and y hat to be close to the joint distribution, the product distribution of x and y with the given distribution p of x and y. And of course, we again use the total variation distance. And the question is, what's the minimum communication rate R needed? Bennett et al. In 2002 showed that the minimum rate is the mutual information. Okay, so actually what they showed is something quite actually more interesting than this. What they showed is that for arbitrary xn, so it doesn't have to be IID with some prescribed distribution for any arbitrary xn, the minimum R is actually the capacity of the channel P of y given x, which is the maximum P of x of I of x and y. And so their interpretation of this result is that a noiseless channel with capacity C and unlimited common randomness can simulate any noisy channel with capacity C. Now, one interpretation of Shannon's capacity theorem is that a noiseless channel with capacity C can be simulated by any noisy channel with capacity C. And therefore, any channel P can simulate a channel Q, provided that the capacity of P is bigger than or equal to the capacity of Q. And in some sense, this says that capacity is the only invariant of the communication channel. And their question was, does the same hold for entanglement-assisted quantum channel? Entanglement is another word for common randomness. And they showed that, in fact, holds for certain classes. OK, now without common, what happens if there is no common randomness between Alice and Bob? What's the minimum rate? Well, it should be larger than the mutual information. It's actually not difficult to show that it's actually the Wyner common information. So it goes from mutual information. We know Wyner common information. And so this is actually shows operationally, without looking at definition, that the Wyner common information is bigger than or equal to the mutual information. Also, if we let x equal y, the problem reduces to lossless compression. So in some sense, this setup is a generalization of lossless compression. Now, so what if we have limited common randomness? We are interested in a trade-off between the rate of common randomness and the rate of communication. And Koff and Bennett et al. Independently and around the same time established the optimal trade-off. And on one extreme, when there's no common randomness, you have the Wyner common information. When you have unlimited common randomness, which is really not unlimited because you know how much you need, you get the mutual information. In between, you have this trade-off curve. And Koff showed some application of this result to information theoretic secrecy. So what about the one-shot case? In the one-shot case, if you have unlimited common randomness, then Harsha et al. Showed that the minimum expected length of the code you need is in between I of the mutual information plus 2 log, and mutual information plus 1 plus some constant, doesn't depend on mutual information. And if we have no common randomness whatsoever, you can easily show that the minimum expected length is between the common entropy and the common entropy plus 1. And for x equals y, the problem reduces to 0 error compression with limit h of x. So this is, again, a generalization of 0 error compression. And the optimum trade-off between R and RC is not known. So to conclude, talked about the limits of randomness generation. We found that the limits on randomness generation and on communication are very closely related. The entropy is the limit on compression and randomness generation. Mutual information is the limit on channel capacity and lossy compression. It's also the limit on channel simulation with common randomness. Wyner common information is the limit on asymptotic distributed randomness generation, and also an asymptotic channel simulation without common randomness. Common entropy is the limit on one-shot distributed randomness generation, one-shot channel simulation without common randomness. And it's very clear that randomness generation is a natural application of information theoretic ideas and techniques. And thank you very much.
Really, I don't have the authority nor the knowledge to give you a lecture about the great master, even though I have read many of his papers that had a profound influence on my thinking. But